Who are we? What is our purpose? Where did we come from? And what is the original source of the energy at the root of human form? These questions are fascinating at the very least. I must admit that as I begin to explore the work of Stephen Hawking, I am exhilarated by the compatibility that may emerge more clearly between the discoveries of modern physics and what sages and mystics throughout history have suggested. In order to share an image that keeps coming to mind, I'll paraphrase Alan Watts. We are all the little curlicues out on the fringes of the original cosmic bang. We are it, not effects of it. In A Brief History of Time, Stephen Hawking moves us through a chronology of discoveries in physics, opening an understanding to how past theories burst open the doorways toward more modern theories. In particular, Stephen Hawking's life endeavor to uncover the corresponding factors between two seemingly different theories in physics, quantum mechanics and the general theory of relativity. Here, I'm reading from the foreword. The success of A Brief History indicates that there is widespread interest in the big questions like, where did we come from? And why is the universe the way it is? I also describe the progress that has been made recently in finding dualities or correspondences between apparently different theories of physics. These correspondences are a strong indication that there is a complete unified theory of physics, but they also suggest that it may not be possible to express this theory in a single fundamental formulation. Instead, we may have to use different reflections of the underlying theory in different situations. It might be like our being unable to represent the surface of the Earth on a single map, and having to use different maps in different regions. This would be a revolution in our view of the unification of the laws of science, but it would not change the most important point, that the universe is governed by a set of rational laws that we can discover and understand. Page 6. It is an interesting reflection on the general climate of thought before the 20th century that no one had suggested that the universe was expanding or contracting. It was generally accepted that either the universe had existed forever in an unchanging state, or that it had been created at a finite time in the past, more or less, as we observe it today. Page 9. One can imagine that God created the universe at literally any time in the past. On the other hand, if the universe is expanding, there may be physical reasons why there had to be a beginning. One could still imagine that God created the universe at the instant of the Big Bang, or even afterwards, in just such a way as to make it look as though there had been a Big Bang. But it would be meaningless to suppose that it was created before the Big Bang. An expanding universe does not preclude a creator, but it does place limits on when he might have carried out his job. Page 12. One of the major endeavors in physics today, and the major theme of this book, is the search for a new theory that will incorporate them both, referring to the general theory of relativity and quantum mechanics. A quantum theory of gravity. We do not yet have such a theory, and we may still be a long way from having one, but we do already know many of the properties that it must have. Page 13. If there really is a complete unified theory, it would also presumably determine our actions, and so the theory itself would determine the outcome of our search for it. And why should it determine that we come to the right conclusions from the evidence? Might it not equally well determine that we draw the wrong conclusion or no conclusion at all? Ever since the dawn of civilization, people have not been content to see events as unconnected and inexplicable. They have craved an understanding of the underlying order in the world. Today we still yearn to know why we are here and where we came from. Humanity's deepest desire for knowledge is justification enough for our continuing quest, and our goal is nothing less than a complete description of the universe we live in. Page 21. As an object approaches the speed of light, its mass rises ever more quickly, so it takes more and more energy to speed it up further. It can, in fact, never reach the speed of light, because by then its mass would have become infinite. And by the equivalence of mass and energy, it would have taken an infinite amount of energy to get it there. For this reason, any normal object is forever confined by relativity to move at speed slower than the speed of light. Only light or other waves that have no intrinsic mass can move at the speed of light. Page 34. The difference in the speed of clocks at different heights above the Earth is now of considerable practical importance with the advent of very accurate navigation systems based on signals from satellites. If one ignored the predictions of general relativity, the position that one calculated would be wrong by several miles. In the theory of relativity, there's no unique absolute time, but instead each individual has his own personal measure of time that depends on where he is and how he is moving. Space and time not only affect, but also are affected by everything that happens in the universe. Just as one cannot talk about events in the universe without the notions of space and time, so in general relativity it became meaningless to talk about space and time outside of the limits of the universe. Page 48. If we add up the masses of all the stars that we can see in our galaxy and other galaxies, the total is less than 1/100th of the amount required to halt the expansion of the universe, even for the lowest estimate of the rate of expansion. Our galaxy and other galaxies, however, must contain a large amount of dark matter that we cannot see directly, but which we know must be there because of the influence of its gravitational attraction on the orbits of stars in the galaxies. Moreover, most galaxies are found in clusters, and we can similarly infer the presence of yet more dark matter in between the galaxies in these clusters by its effect on the motion of the galaxies. When we add up all this dark matter, we still get only about 1/10th of the amount required to halt the expansion. However, we cannot exclude the possibility that there might be some other form of matter distributed almost uniformly throughout the universe that we have not yet detected, and that might still raise the average density of the universe up to the critical value needed to halt the expansion.